Welcome, ladies and gentlemen, to this video lecture. Okay, so now we will move on to an extremely important concept in all of mathematics called the comparison test. So this is the principle behind it is quite easy to understand. So what I will do now is I will just explain the basic principle behind it, behind how the comparison test works. So let's say, for example, you have some very complicated shape A that has, let's call it A. It's very complicated. But if we know that this shape is contained in a square with side lengths 1 unit, we know something about the area of this shape A. Area of A, we know that it is less than 1 because the square has area 1. And similarly, if we have some complicated shape B and we know that B, or we can fit a square of side length 1 inside of B, then we know that we know something about the area of B. We know that it is bigger than 1. So the principle here is we can compare the areas of complicated shapes to simpler ones. And even though we don't know exactly what the area of A and of B here are, we can find a bound, either upper or lower, on what the area is. So if A fits inside the square of unit 1, we know that A has area less than 1. If we can fit a square of with side lengths of unit 1 inside of B, we know that the area of B is bigger than 1. So even though we don't know what the area of B is and what the area of A is, we can say that it is less than 1 or it is greater than 1. Okay, so this is the principle involved. We want to compare the areas of complicated shapes with simpler ones. So here we compare these complicated shapes with unit squares. So this is the idea behind the comparison test. Okay, so let's write down the comparison test. Theorem. Let A be some real number. Let f and g be defined on the interval from a to infinity. And let them be continuous. And assume that for some c, so some point c in the real numbers, we have that 0 is less than f of x is less than g of x for all x greater or equal to c. Okay, then number 1, if the integral from a to infinity of g of x dx converges, then the integral from a to infinity of f of x dx converges. And number 2, if the integral from a to infinity of f of x dx diverges, then the integral from a to infinity of g of x dx also diverges. Okay, so before we go on, let us just discuss what this means. So let us discuss case 1. So we've got, let's say we have two functions that does their thing, and from some point onwards, c, g is bigger than f. So from c onwards, let's say if we draw the graph of g and of f like so. So from some point onwards, f takes on values greater or equal to 0, and g is bigger than f. So this is what this condition says here. So for all x bigger than c, if we have that 0 is less than or equal to f of x is less than equal to g of x. So from the point A, here the functions can do anything, but from some point c onwards, our functions are in this relationship that the values of f is less than equal to the values of g, and everything is greater or equal to 0. Then, if we go and we compare the integral of g, so from c onwards, we see here that if we compare it to the integral of f from c onwards, the integral of f is going to be smaller than the integral of g. And so if g converges, that means it converges to some finite value. That means that the integral of f from c to infinity is going to be smaller. It's going to be greater than or equal to 0, but is going to be smaller than the integral of g, meaning that it will also converge. And if we then add the extra parts here that we are disregarding, since these numbers are finite, we can conclude that f also converges. So if g converges, then f also converges. Oops, sorry, I made a mistake. No, that is correct. Okay, so that is situation 1. Let's talk about situation 2. So we have some point c, so that afterwards, so after the c, again g takes on a value that is bigger or equal to the values of f, and everything is greater or equal to 0. So now, if we look at the statement 2, if the integral of f diverges, then the integral of g diverges. So how does that work? If the integral of f diverges, that means this integral from c onwards, this is going to have infinite area. But the integral of g is going to be even bigger. So the integral of g will also be infinite. So therefore, if the integral of f diverges, that also means that the integral of g will diverge. Okay, so what is the use of the comparison test? So for example, if you have some simple function, some very simple function g, which you know that it converges, so the integral of g up to or going to infinity converges, and you have some, it is bounding some very complicated function whose integral is very difficult to compute. If you know that g is always greater than this complicated function and g converges, then the integral of f of the complicated function, you know that that guy will also converge. You don't know what it will converge to, but you know that it will converge. But that is half the battle. Once you know that it converges, and you cannot determine its integral analytically, you could at least, you know that it converges, so you could try to compute it numerically. On the other hand, if you have some rather complicated function g, and you can compare it to a much simpler function f, and you know that the integral of f up to infinity diverges, so there is an infinite amount of area below the graph of f, then we also know that there is an infinite amount of area below the graph of g, and therefore the integral of g will diverge. So the idea here is to gain information about rather complicated functions by comparing them to simpler functions. Okay, and in the next video we will take a look at some examples. I will see you in the next one.